Until now, we've calculated energy due to gravity as mgh. That's the mass of the body multiplied by 9.8 multiplied by the height it is above the Earth's surface. Now that works perfectly well as long as we have a body that is very close to the surface of the Earth, because when it's near the surface of the Earth, the force due to gravity is equal to 9.8 times its mass. So the energy due to gravity is equal to 9.8 times its mass times its height. That only works for very small heights. If you're to take that body and move it farther away from the Earth, or to find its gravity with respect to a different planet or, say, the sun, all of a sudden mgh no longer works. So what we do instead is we consider how much energy would there be if that body was infinitely far away from the Earth. So let's say we were to take this body and we were to move it infinitely far away. That's going to be the maximum amount of energy possible because it has the farthest to fall. We call that maximum amount of energy, surprisingly, we call that zero. We say if it's infinitely far away, that the gravitational potential energy is zero. And then, as a body falls, as it gets closer and closer and closer to the Earth, the amount of energy goes down because it has less of a distance to fall. When it's infinitely far away, that is the farthest it can fall from. And as it gets closer, it has less and less energy. It gets converted into, say, kinetic energy as it falls, but has less and less gravitational potential energy until it gets to its lowest point when it hits there. So the way this ends up working is that energy becomes a larger and larger negative as you have less and less energy. The mathematics for dealing with this is based on the way we calculate the force due to gravity. Remember that the force due to gravity is G m over r squared, where r is the distance. So if r is this distance between, well, this is our small mass and that's our large mass, G is Newton's universal gravitational constant, which is 6.67 times 10 to the negative 11. It's this tiny number because gravity is very weak compared to other forces. So that's 6.67 times 10 to the minus 11. And the force due to gravity is G times the mass of each of the bodies divided by the square of the distance between them. As the body gets farther and farther away, that energy goes up until we get to its highest point, and at its very highest point, when it's infinitely far away, we call that energy zero. How much work does it take to get a body from infinitely far away to this closer distance r? The work is actually negative because gravity is going to pull the body from infinitely far away over to here. So as gravity does that, the work you would have to do to the body to get it to stay still here instead of having it accelerate as it falls would be in the other direction. So you would have to push back. You'd have to push back this way as the body moves from here to here. You would have to push back, doing negative work to slow it down, to get it from infinitely far away to here. The amount of work you do to the body is going to be equal to its change in gravitational energy. And so we'll use that work to find out what the gravitational energy is at this point. And then if you find the gravitational energy at one point and find the gravitational potential energy at another point, the difference between those two would be equal to the change in gravitational potential energy which can be used as the increase in kinetic energy as a body falls. Okay, so here's how we calculate this. So we have our large mass, and infinitely far away, we have our small mass. It's a distance that's infinite. And then we're going to look at the work that we must do as that mass makes its way towards the larger mass. So that mass is now going towards this larger mass to this distance r away. And if you were to just let go, that mass would fall towards this one, and it would accelerate. It would go faster and faster and faster. How much work would you have to do to that body to get it to go from infinitely far away to a distance r and stay still? To get it to stay still, you would have to exert a force pushing against gravity to allow it to fall at a very slow, constant rate. And the closer it gets, the greater that force is going to have to be. So the negative work you do to take the body from out here to a distance that's closer here is going to be equal to the force multiplied by the distance. But the situation is slightly more complicated because that force depends on distance. So all of a sudden you have this changing force that's being multiplied by the distance. So if the force is changing, you must ask yourself, well, which force value do we use? That changing value, you can't use the average because it doesn't change at a constant rate. That force is equal to G m over r squared. So if you were to plot it, you would see that when you are really far away, the force is tiny. See, this is our distance away, so this is our r value, and here's our force value. And when you're really far away, that distance is tiny, and then as you get closer, it gets larger and larger until it's arbitrarily close. So let's say you're going from infinitely far away to some distance away, and we're calling that r. To multiply force by distance, you were actually multiplying many forces by many small distances, and we're adding them together. So these little rectangles I'm drawing under that curve represents the force distance product, which is work, as we make our way from infinitely far away all the way to r. Now, the width of these rectangles give us a little bit of inaccuracy. See how we're kind of overestimating here, maybe underestimating there? The wider those rectangles are, the less accurate we are. The more narrow they are, the more accurate we are. And if we could get them to be infinitely narrow in width, then we would have the exact value for the area under this curve, and that exact value would be equal to the work that has to be done to get the body to move from infinitely far away to a distance r away from the center. There's a little trick in math that allows us to do this. Remember how when you learn to find slope, you would take the derivative of a function, and the derivative would give you the slope or the rate of change of that function? If you go the other way, if you do the opposite of taking a derivative, that is, if you find the function whose derivative gives you that function, that will give you the area under the curve. And that's the approach that we use to find work due to gravity. In fact, it was invented for this. So let me just quickly go through how to do that. We have this curve, and the function is g m over r squared. It's our changing force. And when our distance to the center is down here, that force of gravity is really high. When we're infinitely far away, it's 0. And then everywhere in between, it follows that curve. And what we're doing is we're finding the work. And the work is the area underneath as we make our way from being infinitely far away to whatever current distance we are away from the Earth, let's say. So we want to find the area under there. Now, just as the derivative will give you the slope, the opposite of the derivative, if you set it up properly, will give you the area. And we want this area to come out as a negative because we're not looking at the work that the Earth does to a body as it falls from infinitely far away to distance r. We're talking about the work we must do to the body to slow it down so that it ends up at rest at a distance r away from the Earth. The way this looks when we set it up, the work is what we get when we add up the force times the distance. And these are like these little mini distances as we go from infinitely far away to our distance r. So that dx, it's the same dx as when you're doing a derivative. You do like dy dx in Leibniz notation. What that dx represents is the width of the little rectangle. That dx is the width of the rectangle, and then f is the height of the rectangle. And when you multiply them together, that's what's happening here, f times dx, we're multiplying to get the area of our rectangle. So the f dx is the area of the rectangle. And this symbol here means let's add up our infinite number of infinitely narrow rectangles, and that's going to give us the area under this curve, which we call the work due to gravity. And it turns out for this particular problem, it's a lot easier than it sounds. So our work is what we get when we add up all the way from being infinitely far away to where we are now, the force. And the force is G. Now, let me erase that. I was writing an F because it's the force. But the magnitude of the force is G m over x squared, where x is our current distance away, and it's making its way from infinity all the way to r, and then we're going to multiply that by dx. So what does that mean? Those terms in the after the symbol, the g m over x squared, that is the height of a rectangle. That's your g m over x squared. And the width of the rectangle is dx. And when you multiply them together, it gives you the area of the rectangle. And what we're doing here is we're adding up a whole bunch of those rectangles. And when we add them together, that's going to give us the area under the curve. The fundamental theorem of calculus tells us that we can do this if we can just guess what function that this is the derivative of. So I'm not finding the derivative of g m over x squared. I'm finding the function that when we take its derivative, we get g m over x squared. It's kind of like you're square rooting instead of squaring, or you're dividing instead of multiplying. You're going the opposite way. So what would give us a derivative of g m over x squared? Well, let's look at that. So let's imagine that some function's derivative is g m m over x squared. And let me rewrite that. Our function's derivative, so that function's derivative is, I'll use my rules of exponents. It's g m m x to the negative 2. Now, when you look at it like this, it becomes way easier to guess what it was the derivative of. Because remember, when you're taking the derivative of an exponent, you bring the exponent down as a coefficient, and then you subtract 1 from the exponent. So when you're taking the derivative of like a term in a polynomial, sorry, it's not an exponent, a monomial. This is physics class, so yeah, we're not going to worry about the terminology, but let's consider this. We need it to end up with a minus 2. So let's say x had a minus 1. That's our first guess. So let's start there. If you take the derivative of x to the negative 1, then that's going to give you negative x to the negative 2. So look at that. We're pretty close here. If you take x to the negative 1, its derivative is negative x to the negative 2. So if you want the derivative to be a positive x to the negative 2, well, all you got to do is make that original function a negative. Now, when you bring that negative 1 down, that becomes a positive. Now, if you want, the derivative of your function to be multiplied by gmm, all you need to do again is just multiply this by gmm. So instead of negative x to the negative 1, it's just negative gmm to the negative 1. So what does that mean? That means that our function is gmm x to the negative 1, which is, sorry, negative gmm x to the negative 1, which is negative gmm over x. So have a close look at that. The derivative of this is going to give you gmm over x squared. Now, this whole problem was set up with this symbol taking us from infinity to r. So what that means is we just take that function at infinity and then subtract that function at r, and we're done. That's going to be the area under the curve. So that function at infinity is going to be negative g m over infinity, and then we subtract from that the function at r, which is going to be negative g m over r. You know what? I think I wrote that backwards. Let me fix that. When our symbol is set up like this, we weren't going from r to infinity, sorry. We were going from infinity to r of that function dx, where that function was gmm over r squared. So what that means is we're going to take our antiderivative, which is negative gmm over x squared. We're going to evaluate that at r, and then subtract the evaluation of that at infinity. So this is going to be F at R minus F at infinity. So that's going to be negative G M M over R minus negative G M M over infinity. And when you divide by infinity, you get 0. So that just disappears. And what we're left with is the area under the curve, and therefore the amount of work, and therefore the gravitational potential energy due to gravity is negative G M M over R. So this formula works no matter where you are, as long as you've got bodies of two different masses, a distance r away from each other. This is how much gravitational potential energy there will be. If it's infinitely far away, you put infinity in for r, you're dividing by infinity, it's 0. So when you're infinitely far away, the gravitational potential energy is 0. And as you get closer, you get a negative. And a larger negative as you get closer just indicates you have less and less gravitational potential energy because you've been falling. So let's find the gravitational potential energy. Let's say you have a planet, and that planet has a mass of 10 to the 24 kilograms. And let's say you are a distance that is 50,000 kilometers from its center. So if you're a distance 50,000 kilometers away, and you have a mass, let's say your mass is 100 kilograms, the gravitational potential energy is going to be G 6.67 times 10 to the negative 11 times the product of the two masses, so that's 10 to the 24 times 100, and then divided by the square of the distance between them, and this is 50,000 kilometers, so I'm going to add 3 more zeros, convert that to meters, we're in SI units here. And we're not going to square that, sorry, that's just our R value. And the whole thing is a negative. So you plug those numbers in. So that gives me a 6.67 times 10 to the negative 11 times 10 to the 24 times 100, and divide that by 50 million. And that's going to give us a gravitational potential energy of negative 1334, and then 5 zeros after it. So this gravitational potential energy is the amount of energy that the body has at a distance 50,000 kilometers away from that planet that has a mass of 10 to the 24 kilograms. I know this is a negative, but if you were to put the body even closer to that, you get a larger negative, which would indicate the energy drop. Okay, let us now consider the escape velocity. So imagine you have a planet here, and let's say that planet again has a mass of, so that planet has a mass of 10 10 to the 24 kilograms. And let's say it has a radius of 7,000 kilometers. So when you're on the surface of this planet, you are 7,000 kilometers from the center. And the planet has a mass of 10 to the 24 kilograms. The escape velocity question is asking, with what velocity must an object be thrown upward from the surface of this planet such that it can get infinitely far away? That is, imagine this. You're on the surface of a planet. Well, you don't have to imagine that. You are on the surface of a planet. So you're on the surface of a planet, and you take an apple, and you throw that apple upward. So you take that apple and why is this rotating here? There we go. You take that apple and you throw it upward. It's going to come back down. If you throw it faster, it's going to go even higher, and then it's going to come back down. The escape velocity is the velocity required for when you throw that apple for it to go infinitely far away. How do you do that? You throw it with such a velocity that its kinetic energy is equal to the gravitational potential energy that you had here. When the kinetic energy is as high as the gravitational potential energy, then it can get infinitely far away. It can escape. And the total amount of energy would be zero. So how do we figure that? How much gravitational potential energy do we have here? Because that's going to be equal to the kinetic energy for that body to escape. So let me list them here. The kinetic energy of escape is equal to the gravitational potential energy. So the kinetic energy of escape, half mv squared, is equal to the gravitational energy, which is m times g over r. You make them equal in magnitude. So what must that velocity be? Well, I'm going to leave it to you to do the work to figure this out. I'll give you a hint. It doesn't depend on the mass of the body. So let's say that's the mass of the apple. It cancels out at both sides. So rearrange this, and when you get v by itself, that will be your formula for the escape velocity. The idea here is that you can escape if you are infinitely far away. And in order to be infinitely far away, you would have to have a gravitational potential energy of zero. Anywhere closer, and the total energy is the negative gravitational potential energy plus the positive kinetic energy. So by setting them equal to each other, you have so much kinetic energy when you're here that as you fly infinitely far away, you can make it to get there so that at that point your energy is zero. So that's an exercise for you to rearrange this, and best of luck on your homework.